Hello and welcome to our manufacturing review. We're the LU Rocketeers and I'm the team lead, Samuel Tigner. Today with us here we have Ant, Shady, and also our vice team lead, Andrew, who will now be taking over.
Hello again. So just to give you a brief reminder then, so these are our goals. So it's to design, develop and manufacture a payload bearing rocket, which is reusable, uses programming models to assist with development and design, reaches an approximate apogee of 2,500 feet or 762 meters, whilst producing high quality deliverables and doing all this on a reasonable budget. Next slide, please, Sam. So this is our project plan. So this is the final iteration of our Gantt chart. So we're currently in the light green section as indicated by the purple arrow. We are finalizing, at this stage, we're finalizing manufacturing and underway with testing during this Easter break. We aim to make a big push when we get back from Easter to finalize this testing, iron out issues that may arise from it, and things like that. We're quite optimistic with our progress and confident that we can make the FRR deadline and also be well prepared for launch week and the launch day. And as mentioned previously, the red columns are when exam season starts. Next slide, please, Sam. So this is our budget slide. So looking at the expenditure so far, we're quite satisfied with the amount. There are obviously going to be bits that we need to add, like the BMFA membership and some other unexpected costs that we might need to take a hit on or endure, but we're looking at sub £500 for the whole project, which everyone is very satisfied with. And just to make a note on this, we'd like to thank the Physics Outreach Department for supporting this, and also fellow team members who have also invested a lot of their time and also some monetary value as well. I'll hand back over to Sam now.
So our options for motor retention are basically boiled down to two things. So we've opted for the motor hardware, which allows us to reload our motors when we've used them, because we've chosen to use the G76G Aerotech motor. So our first option is basically that we just use ring retainers that can be purchased online and adapted between our 29mm hardware tube and our main body tube. But we also have this second option, which involves printing a part that fills that cavity void space in between the tubes. So to explain that a little better, I've got some diagrams here. So you recognize this on the slide. So we've got the hardware tube below and also a little diagram of the cross section on the right. So from the rear view of the rocket, we basically have this gold retaining ring, which has two slots. Those slots are meant for retaining bolts, but what I've opted to do is use a 3D printed part on the left here. So the smaller part is like a little lock mechanism. So it's got the notches to fill the slots, and then that will basically go in over the top of the gold ring and into this larger part, which will fill the space in between the two tubes. So the impact of this choice is actually quite severe, because that part, if we choose to keep it as dense as it is, will weigh about 56.5 grams, which is a bit unsuitable because it means that it will offset the center of mass towards the back of the rocket and make it less stable, which means that there is potential that we might actually fail the stability requirements, only by a margin of about 0.07, but this can be amended by making the part lighter and also focusing more of the weight of the rocket into the nose instead of the rear. So we're still on target to reach an apogee of somewhere in the region of 730 meters, but we want to be a little bit higher than that. So I'm now going to hand over to Ant.
So what Sam was explaining before was more to the side of the retention side of things. So the ASA, the actual rocket tube itself, where you can see in front of you, is being manufactured at the moment. So we're working with technicians currently using sort of their expertise combined with our own to try and mitigate sort of the learning curve that you have with using new filaments. So ASA is quite temperamental filament to print with. It's got quite a lot of warping issues. You need to let it cool down. It's also very struggles to stick to the bed. The reason why we're using ASA, as we've come about before, was due to its better thermal properties and lighter density as well. So it's been quite temperamental to print with. So can I have next slide, please, Sam? So this is what our first print was to try and mitigate it. So we've got a massive ring at the bottom. That's to stop it from falling over. And we've also got tree supports within the center. So this print failed. Not quite sure why yet, because we've got to get the pictures from the technician to come back. And we'll see what's gone wrong and then adjust our parameters accordingly. Moving on to the next person, Sam.
So as Ant has mentioned, we have had quite difficulties with ASA, and so looking at our options, material selection, we had PLA, ABS, and PLA is great, as Sam is going to show you. It's great for prototyping. It's quick and easy and pretty cheap. But we wanted to use ASA as it has better lower density, and its impact resistance is quite higher. But as Anne mentioned, it can be quite particular. So we were looking for other options. Another option is a selective laser sintering, SLS, and using the SPRO 63 printer, and it will sinter nylon. And in terms of its density, it's better than ASA and PLA, and its impact resistance and tensile strength is quite high. So it makes it the best candidate for structural and load-bearing parts. And in general, it could be a great option. But there are some issues with it. Can you go to the next slide? In terms of printing it, because it's sintering it and the way the machine is, the exterior can be quite rough, which can mess with the aerodynamics. So what we need to do is sand it pretty well, but that should be a simple job. And in terms of painting, we could paint it. And if you need a primer, we'll just use that, and it'll give you a uniform finish and some extra protection potentially. On to the next slide.
So now I'm going to do a quick demonstration. So as you might recognize from the CDR, I've got some prototype parts here that Shady mentioned briefly. So basically this is just going to be a little demo of how everything's put together. So within this main top tube here, the payload bay, we have the two payloads. So the customer payload will go at the front here and the ride share payload at the back. So the customer payload will slot in and interface with the LVA, which is actually right at the top here. And then everything else slots completely together flush like this and is held together by friction. So here we've got the camera holes and all the M3 bolt holes that are necessary for retaining the parts, and also from the bottom here as well we'll put all the bulkhead and the ejection charge. We also have a hole here for the temperature and humidity sensor that we've opted for, which slots in as so. So now I'll switch back to the slides. So as far as our rideshare payload manufacture is going, it's been quite slow because we're on Easter break and we don't have the facilities to solder it all together yet. What progress we have made is we've managed to solder the grissom, which was quite difficult because obviously it's very small. We had some assistance from a technician to supervise us doing that, so that's all been completed. But as far as assembling the rest of the circuitry goes, we have yet to start because we need to acquire the power supplies for that and then put that all together. But it should be quite straightforward because everything will be 3 separate circuits, all powered separately and isolated from each other as per the technical specification. For the rest of the testing, we're going to push that back until after we get back from the Easter break so that we can get as much of the team together as possible and put all the rocket together. And once all of the ASA parts have finished printing, we can do all of the load-bearing tests on those. So that should help us complete at the very least the bottom half of this table here. So thanks for watching our manufacturing review.